Welcome to a deep dive into the frontiers of physics. Today, we are journeying into the cavernous, complex halls of CERN's antimatter factory in Geneva. It is here that a collaboration of physicists known as AEgIS recently achieved something that was considered impossible for decades. They used a laser to cool down positronium, an exotic, fleeting atom made of both matter and antimatter. By slowing its frantic dance, they have potentially unlocked the deepest secrets of the universe. This is a story about the mirror universe, the ghost atom, and the technology that might one day allow us to break the laws of physics as we know them. To understand the magnitude of this achievement, we first have to grapple with the substance itself, antimatter. It sounds like science fiction. It is the fuel of starships in Star Trek, and the destructive force in Dan Brown novels. But it is very real, and its story begins in 1928 with the British physicist Paul Dirac. Dirac formulated an equation that combined quantum mechanics and special relativity to describe how an electron moves at high speeds. The equation was beautiful, but it had a strange quirk. It allowed for two solutions. Think of it like the simple math equation x squared equals 4. That equation has two answers, 2 and minus 2. Dirac's equation was similar. It predicted an electron with positive energy, which makes sense, but also an electron with negative energy. This negative solution was the mathematical birth of antimatter. Dirac realized that for every particle of matter, there must exist a mirror particle with the same mass but opposite electric charge. 4 years later, Carl Anderson proved him right by discovering the positron, the antimatter twin of the electron, in cosmic rays. This discovery completely upended our understanding of reality. We learned that if matter and antimatter meet, they annihilate instantly. They vanish, releasing their mass as pure energy according to Einstein's famous equation, E equals mc squared. This volatility makes antimatter the most potent energy source known to physics. It also makes it the most elusive substance to study. And this brings us to the great cosmic mystery. The existence of antimatter poses one of the biggest unanswered questions in cosmology. Where is it? According to the Big Bang theory, the universe should have been created with equal amounts of matter and antimatter. If they were created equally, they should have annihilated each other in the first instance of the universe, leaving nothing but light. But that did not happen. Matter won. Everything we see, from the stars to the device you are listening to right now, is made of matter. A tiny asymmetry allowed a fraction of matter to survive. Physicists believe that the keys to understanding this asymmetry, and thus our very existence, lie in the subtle differences between matter and antimatter. To find those differences, we must measure antimatter with extreme precision, and to measure it, we must catch it. This brings us to our protagonist, the ghost atom, known as positronium. While antihydrogen is the most famous antimatter atom, positronium is unique. It is purely leptonic. It has no nucleus. It consists simply of an electron and a positron orbiting each other. It is a system of pure balance, matter and antimatter dancing in a vacuum. Because it has no protons or neutrons, which are made of quarks, positronium is free from the messy, strong nuclear force interactions that complicate the study of heavier atoms. It is the perfect laboratory for testing quantum electrodynamics, the theory of how light and matter interact. However, positronium has a fatal flaw. It is suicidal. Since it is composed of a particle and its antiparticle, they are destined to collide and annihilate. There are two states of positronium. The first is parapositronium. In this state, the spins of the electron and positron are opposite. It lives for a mere 0.125 nanoseconds before annihilating into two gamma-ray photons. The second state is orthopositronium. In this state, the spins are parallel. It lives roughly 142 nanoseconds before annihilating into 3 gamma rays. That is the window physicists have, 142 nanoseconds. That is all the time they have to create it, study it, and manipulate it. To make matters worse, when positronium is created, usually by firing a beam of positrons into a target, it is incredibly hot. The atoms move at tremendous speeds, bouncing around randomly. This thermal motion creates a Doppler blur, making it impossible to measure their properties with high precision. For 30 years, physicists have dreamed of cooling positronium. If they could slow it down, they could measure its spectral lines, its fingerprint, to see if it behaves exactly like the standard model predicts. Any deviation could reveal new physics. But how do you cool something that vanishes in the blink of an eye? This brings us to the Cold War of physics and the revolution of laser cooling. Laser cooling is one of the triumphs of 20th century physics, earning the Nobel Prize in 1997. The concept is counterintuitive, because we usually think of lasers as things that heat or burn. But if tuned correctly, a laser can freeze atoms in their tracks. Here is how it works. It relies on the Doppler effect. Imagine an atom moving toward a laser beam. If the laser is tuned to a frequency slightly lower than what the atom likes to absorb, the atom won't interact with it much when standing still. However, if the atom moves toward the laser, the Doppler effect shifts the light's frequency up, blue shifting it into resonance. The atom absorbs the photon and receives a tiny kick of momentum backward, slowing it down. It then re-emits the photon in a random direction. Over thousands of cycles, these tiny kicks bring the atom to a near halt. Applying this to positronium seemed impossible for three main reasons. First, mass. Positronium is incredibly light, about 1/2000th the mass of a hydrogen atom. This means every time it absorbs a photon, the kick is violent. It is like trying to slow down a ping-pong ball with a fire hose rather than a bowling ball. The recoil is massive. Second, time. Normal atoms can be cooled over milliseconds. Positronium dies in nanoseconds. You do not have time for the thousands of gentle cycles used in standard laser cooling. You need to cool it instantly. Third, wavelength. The laser light needed to cool positronium is in the deep ultraviolet spectrum at 243 nanometers. Creating a laser that is powerful enough, pulsed correctly, and tuned to this difficult wavelength is an engineering nightmare. For decades, this was the final boss of atomic physics. Many theoretical papers were written, but the experimental hardware simply did not exist. Enter the AEgIS collaboration. Located at CERN's antiproton decelerator facility, AEgIS is a collaboration of physicists from across Europe and India. Their primary goal is actually to test gravity. They want to know, does antimatter fall down? According to Einstein's weak equivalence principle, gravity should affect all mass equally. But some theories suggest antimatter might experience anti-gravity, or fall at a slightly different rate. To test this, AEgIS wants to make antihydrogen atoms and watch them fall. To make antihydrogen, they smash antiprotons into a cloud of positronium. This reaction works much better if the positronium is moving slowly. If the positronium is zooming past the antiprotons too fast, they miss each other. Thus, cooling positronium became a critical technological milestone for AEgIS. The breakthrough happened in February 2024. The team utilized a novel approach that broke from tradition. Instead of using a standard continuous wave laser, which is too slow, the team developed a special broadband pulsed laser. Here is the step-by-step process of their experiment. First, the source. They generated a beam of positrons using a radioactive sodium source and guided them into a magnetic trap. Second, the target. They fired the positrons into a nanotarget made of porous silica. Inside the tiny pores of this glass-like material, the positrons stole electrons from the silica atoms, forming positronium. Third, the cloud. The positronium atoms drifted out of the silica into a vacuum chamber. At this point, they were hot, moving at typical thermal speeds. Fourth, the laser strike. This was the magic moment. The team hit the cloud with a custom-built Alexandrite laser system. Unlike standard cooling lasers that use a very narrow frequency, like a single pure note, this laser was broadband. It covered a wider range of frequencies. Why broadband? Because positronium is so light and moves so fast. The Doppler shift is enormous and varies wildly from atom to atom. A narrow laser would only talk to a tiny fraction of the atoms. The broadband laser was like a choral shout, able to interact with a large percentage of the fast-moving clouds simultaneously. The result was staggering. In just 70 nanoseconds, less than the blink of an eye, less than a lightning strike, the laser plummeted the temperature of the positronium cloud from 380 Kelvin, which is over 100 degrees Celsius, down to 170 Kelvin, or minus 103 degrees Celsius. It may not sound like absolute zero yet, but in the world of antimatter physics, this is a landslide victory. They effectively halved the thermal energy of the system before the atoms could annihilate. They proved that the violent recoil of the light atom could be managed, and that the cooling could happen faster than the annihilation clock. Science is often a race, and remarkably, AEgIS was not alone. Around the same time, a team from the University of Tokyo achieved a similar feat using a different method called chirp cooling. While AEgIS used a broadband hammer to cool the cloud for anti-hydrogen production, the Tokyo team used a chirped laser. This is a laser where the frequency changes rapidly over time to track the atoms as they slow down. The Tokyo team managed to cool the atoms to around 1 Kelvin, a much lower temperature, though with a different density and setup. Far from being rivals, these two results complement each other perfectly. AEgIS demonstrated the robust, high-yield cooling needed for making antimatter beams in factories. The Tokyo team demonstrated the deep freeze cooling needed for ultra-precise measurements. Together, they have kicked open the door to a new era. So why does cooling a ghost atom matter to the average person? Why does this change everything? It is the first step toward technologies that sound impossible today. The first implication is the gamma-ray laser. This is the holy grail application. Conventional lasers use electrons jumping between energy levels to emit light. A gamma-ray laser would use the annihilation of matter and antimatter to produce a coherent beam of high-energy gamma rays. Until now, this was fantasy. To make a gamma-ray laser, you need a Bose-Einstein condensate of positronium. This is a state of matter where all the atoms cool down enough to sync up and act as a single quantum wave. Once you have this condensate, the atoms could be triggered to annihilate in unison, releasing a focused, coherent pulse of gamma radiation. Such a laser would have a wavelength orders of magnitude smaller than visible light. It could allow us to image the nucleus of an atom, just as optical microscopes see cells. It could revolutionize radiation therapy by targeting cancer cells with subatomic precision, sparing healthy tissue entirely. It could even allow for nuclear communication through solid rock or water. The second implication involves testing Einstein and gravity. As mentioned, AEgIS wants to know if antimatter falls up. If they find even a tiny difference in how gravity pulls on antimatter versus matter, it would break the general theory of relativity. It would imply a fifth force of nature, or require a complete rewrite of our understanding of the universe. Cold positronium increases the production rate of antihydrogen, making these gravity experiments feasible in the next few years rather than decades. The third implication is cracking the code of the universe regarding Kapton symmetry. The standard model relies on the idea that if you swap charge, parity, and time, the laws of physics stay the same. If we measure the energy levels of cold positronium and find they don't match the predictions for hydrogen perfectly, it implies Kapton violation. If Kapton is violated, our entire framework of physics is wrong. It might explain why the universe exists at all, and why matter defeated antimatter in the Big Bang. The successful laser cooling of positronium is not just a technical footnote. It is a gateway. We have moved from the era of observing antimatter to the era of controlling it. In the immediate future, we can expect labs to race toward creating positronium Bose-Einstein condensates. We will see anti-hydrogen factories ramp up production at CERN. We are now zooming in on the fine print of the universe's rulebook. For nearly a century, humans have looked at the equations of Dirac and wondered about the mirror universe. For 30 years, experimentalists have banged their heads against the wall of thermal motion. In 2024, that wall crumbled. We have tamed the ghost. Now, we get to see what it can do. Thank you for listening to this deep dive on G Fun Facts Online.